Hey everyone, welcome. I'm so glad to see you all here. It's great to be back after last year's Kafka Summit Bangalore. It's great to see so many people once again. Today I'll be talking about somewhat of an exoteric topic. I'll be talking about an alternate way of generating events or building an event-driven architecture, where primarily we look at generating events right out of an API gateway, or rather just using APIs. And we'll also see how we can use Kafka Streams to transform those events and make them available for consumption. This is a show me how session. That is, there will be a lot more demo than the slides. But I want to set some context before we dive into the demos. So we'll talk about what, why, and primarily why rather than more than how, because the concepts behind why we are proposing this is important. Quick introduction, I'm Avinash. I work at Platformatory as a platform engineer. I'm also a Confluent community catalyst. I'm involved in quite a few communities. I'm available on LinkedIn, or please send me an email. I'm happy to connect post this talk. Right? Okay, let's begin with something that we see every day. Most people might be familiar with RPCs, where you make a request to a service, where a client makes a request to a service, and it immediately gets a response back. Although might not be immediate, but it can certainly gets a response back within a time limit. There's some temporal coupling between the client and the server. Let's take an example of creating an order. So when a client initiates a create order RPC, the server responds back with the order created response. So the client knows that there is an order that was created, and it's mostly a privileged transaction between the client and the server. What this means is there's immediate feedback loop for the client. So as soon as the client sends a request, it can expect a response immediately, or maybe with a slight delay. Now let's contrast this with a messaging-oriented approach, where a client produces or generates an event or puts an event into a broker queue. It can be any event broker such as Kafka or the likes of it. And the event from the event broker is then consumed by multiple interested parties who process the event at their own time, and the client here does not really get a response immediately of the request that it made. It receives an acknowledgement, but not a response. That is, there's no immediate feedback loop involved here. The client will have to eventually understand whether the order was created or there's something that went wrong with creating the order. This allows us to scale the consumers independently. That is, the parties who are interested in knowing that an event was created, those can be scaled independently, and there's decoupling between the client and the server. This is also a fairly common pattern. Of course, we're here at Current. We are all very familiar with what Kafka is, and this is the principle behind, one of the principles behind it, right? So the point that I want to get to is the synchronous feedback is very intuitive for when there is an user involved or when there is an external actor involved. That is, you, for example, you place an order on a website, and you immediately expect to see a response saying the order was placed. You do not expect it to be loading for a lot of time, for a long while before it actually says that the order was processed or the order was placed. So whenever there's an human involved or there are external actors involved, you would want the response to be immediate, and so that there is some confirmation that the request did succeed, right? Now, once again, on the other hand, comparing this with our messaging API, there is no immediate feedback loop. What this means is this is primarily an approach where you have a shared journal between multiple coordinating services that understand each other and can coordinate through such messages that are return to a shared journal. And when you want to talk to services that are outside of the bounded context of a service, then this is a fairly common approach where you can, where you have a shared journal and the services coordinate among themselves, and all you get is an event that is saying an order was placed. But then was the order actually placed? That was not something that this concerns with, right? In terms of from the client's perspective. Now, we previously saw a very generic version of an RPC where a client made a request to a server and immediately got a response back. Now, let's see that from a more REST perspective, although it looks exactly the same. But here, there's the REST semantics involved. That is, you post an order, you post /orders, and you get a response back with the order body. So this has certain semantics involved, where you define how should the API look like. You immediately get a response back with the entire order body. So this is how a REST API would look like. Quick show of hands. How many of you all here use REST APIs? And so that's everybody here, right? So you're in the right place. So I want to talk about how you can think about generating events from a REST context, and how do you achieve that, right? So often in real-world scenarios, you will require a combination of both. That is, it's not just a request response or purely messaging. You need a combination of both. Like I previously mentioned, when there's an external actor involved, you would want an immediate response. That's where request response is something that is applicable. But when you are coordinating between multiple microservices within outside a bounded context, you need a shared journal, an internal journal which has a list of messages that were produced, and you can then consume from them, right? So in real world, often from our experience, we've seen that it needs a combination of both. That brings us to the point of today's talk. How do you achieve this? What are the patterns that are available, and what are and there's a new pattern that we're suggesting as well. So we'll talk about the existing patterns on how do you achieve this combination of both request response and messaging in the real world. So the first pattern, which is fairly common, is the database write-through pattern, where you have a service that writes to a database of sorts, and you then capture the changes from that database using a CDC-like mechanism, which then writes it to an event broker. So here, the service does not produce or write to the event broker directly. Rather, it writes to the database, and then the changes from the database are captured using change data capture and returned to a messaging journal. We'll talk about some of the pros, cons later, but let's get through the patterns available, and let's talk about a couple of concerns of one might have using these patterns, and we'll talk through some solutions. The other pattern is the database write-aside pattern, where the service not just writes to the database, but also writes to the messaging queue at the same time. The process here is rather straightforward, where the service first initiates a transaction before it writes to the database, then writes it to Kafka or any message broker for that matter, which supports transactions, and then commit that transaction to the database. So if either of the actions fail, then the database transaction is reverted. But this is not as easy or straightforward to implement as it is as said. There are a couple of concerns with doing such patterns, or rather not specifically to those patterns, but just implementing the whole combination of request response and messaging. There are a few concerns that arise. One of them is how do these services coordinate amongst themselves when there is a shared journal of messages? How do the services coordinate amongst themselves to know that there was something that happened and there are a few things that needs to follow through? One of the concerns is the integration, right? There are two ways of achieving this. One is there's an external system that coordinates these messages amongst the various services that might be in different bounded contexts. So this is nothing but orchestration. Or there is another approach where the services coordinate amongst themselves using a shared journal where the services take the responsibility themselves to do the coordination. That's choreography. There are various reasons why one would choose one amongst the others, but we'll talk about how these can be implemented with a different approach altogether. The other concern here is with eventing is what kind of events do you generate. So primarily, you can classify events into these 3 buckets. There's the light events or the thin events, which just talk about an event occurring, that is, an order was placed. There's no real detail about the order or more information about the order. So it's just a notification of something that happened. And there are the fat events, which are a little more popular, where you see complete details about the event. Let's take the order example again. So if an order was placed, you get the complete details about the order, who placed the order, what were the items, the inventory, the price, everything that is needed for processing that order. So these are fairly common, but of course, these also come with some certain challenges. You do not want big payload sizes. The other kind of events is the delta events, which talk about the changes that happen to a resource. Maybe somebody updated their email or any particular resource that was updated. You're not interested in knowing the entire resource information. Rather, you might be only interested in knowing what changed. So based on what changed, there might be certain actions that you might have to trigger. So in such cases, delta events, or also more popularly known as the CDC events, those are pretty helpful. So why does the event weight actually matter? So why is that a concern? The event weight actually dictates what kind of work that needs to be done. For example, if it's a thin event, then you will have to go coordinate with other services to actually get the right set of information. Just knowing an event happened might not be helpful. You'll also need to know what happened, or rather more context about the event itself. And with CDC events, then it's you typically get a row-level change. That is, you get what is changed, but then you also might get the entire row data that was changed, which results in a fat event more than a thin event or a delta event. Thin events are very low on surface area, but then that also means they lack all the context. Fat events, while it has all the context, but it might be too heavy for one to process, might not be necessary as well. So I want to talk about how this ties up with the REST APIs. So REST APIs are typically fat events. That is, when you do /orders, post/orders, you get the entire order body as the response, which means it's a fat event. There's a lot of overhead with the payload size. How do you manage schema for the entire payload, etc. But when there's also additional temporal coupling between the services in case of REST. So when you contrast eventing with REST is nothing but representational state transfer, so which is usually fat events and stateless. So what this means is doing change events on such REST APIs will event in much fatter events. So if you're doing CDC on REST events, there's a pretty good chance that the resulting event is much fatter, because you capture both the before and after for that particular response. So the events carried state transfer would be the right terminology in the eventing world for such events where you describe how something changed, but at a resource level, right? Now, getting to the point of today's talk, we'll talk about how do you achieve such eventing at the API gateway. We'll talk about how do you generate the various kinds of events, and how is this different from the other approaches that we just saw, right? So let's talk about how this works. Typically, all APIs might be exposed through an API gateway in most real-world scenarios. So you have some proxy that proxies all the APIs, and we have something that can hook into those common API gateways or proxies, capture the request response data from those proxies, and then transform and make them available for consumption using various modes possible. So what this means is, without changing the service itself, right out of an API gateway, you can emit or generate domain events without having to do CDC at a database level. And this also has flexibility of how do you define your event. We'll talk about how during the demo, but the essential idea is you can generate events, domain events, right out of an API gateway without having to do CDC or dual rights, etc. So how is this useful? This integrates really well with REST APIs. So it can, since REST APIs contain the entire context of a resource, either in the request or in the response, you get the entire context of the resource, which means you can capture all necessary data without having to do a DB lookup or do CDC. This also means there's no code changes. You do it right out of an API gateway, which is somewhat common practice where you're using or exposing APIs. And you don't need to do any database level changes or enable any CDC connectors. Although CDC is great at what it does, but there are a few concerns with one might have with using CDC. This also means you can still emit Debezium-styled CDC events, but without having to go through the process of actually setting up CDC and having to do it at a database level. There are a few possibilities that emerge out of it. One of them is, let's suppose you have a slow API that takes a lot of time to respond before it while processing the request. In such cases, with such a pattern, you can immediately return a response, and using the event that is generated, you can then process the event at a later time and then do webhook calls back to the client to update that the response with the actual response and still achieve what you wanted to earlier. There's also a new set of RPCs that are evolving for doing long-running workflows or long-running processes. This particular pattern can also help with building such long-running workflows where you initiate the workflow and capture the event from the workflow that was initiated, and then synthesize those events eventually at a later point of time. And so this can also be achieved in two variations, that is similar to the database write-aside or database write-through and database write-aside patterns. A similar approach here would be the gateway write-through or gateway write-aside. That is, what happens if the gateway crashes before it can synthesize the events? This would mean that we will lose the event. So even at gateway level, you can have transactional semantics with something like Kafka. You initiate a transaction when the request hits the API gateway, and commit the transaction once the response leaves the API gateway, and usually when you're logging the request. So most API gateways have various phases in which the request is processed. So there's a phase, the final phase of most such gateways would usually be the log phase, where after the response is sent back to the client, you get to capture both the request and the response. So that is where we hook in and capture such requests and responses and generate events out of it. You can also achieve optimistic concurrency for an eventing store by using HTTP e-tags. So you have a common ID, a uniquely identifying string that can allow you to actually achieve optimistic concurrency in the eventing world. And finally, you also get a audit of what were the request responses that went out, and you get to capture what were the resource level changes that happened to resources within your environment. Okay, now to the demo. I'll briefly talk about what the demo involves. So we will be using Kong as an API gateway in the demo, but this works with other API gateways as well, where we've tested it against multiple API gateways. Once we capture the request response, we use Kafka Streams to process, filter, transform, and generate change events. And this also means you can do and then fan out these events to multiple processes. Now, without further ado, I'll jump into the demo. Okay, I have a simple setup here. I have a single broker that is running in Docker Compose. I have my gateway, Kong gateway, and we're calling it eventception. The actual process that takes care of processing the events and generating events out of it. Let's see if everything is healthy. Now, I have a few scripts that can help me generate a few events. I'll talk through how this whole thing works, but I'll first run through the demo. I'm generating a few order events. These are all mock data that is going through the API gateway. Sorry. Sorry, I need a reliable connection. Okay, yes. Okay, so we've produced a few order events. Let's also produce a few updates to those. We'll be updating those order events as well. This is to essentially look at how we can emit change events. And let's stop this. Finally, I can consume those change events. Okay, first few were broken due to the bad internet connection. Okay, well, let me just start afresh. Sorry, live demos never go as planned. Okay. Oh, I'll create a few update events. And now we should be able to consume a few messages. Okay, the formatting is off, but the essential event that we get over here, maybe if I can copy one of those events. Okay, yeah, this is one of those events. Sorry. Okay, anyway, so the event that was generated it contains both the before and after in a Debezium styled JSON event, which means you can capture the before the resource that was before the request was made and after the request was made, similar to how you get it with CDC, but without actually doing CDC. Now let me actually talk through how this whole thing works. We have a K-Streams application that, since I've opened this, let me just show it here. So we have a K-Streams applications that has a configuration interface, which takes a YAML configuration to read the events that are generated out of the API gateway. The events are generated out of the API gateway. In the case of Kong, it is through a Kong plugin, which produces the events to Kafka in the log phase of Kong. And similarly, other gateways can also do a similar thing. We've done it with Nginx, Envoy, and the likes of it, where it produces a message to Kafka in the log phase, where it captures both the request and response. And in our Kafka Streams application, or rather it's a wrapper on top of Kafka Streams, which consumes from those messages that are generated out of the API gateway and defines a few topologies. These topologies are dynamic, that is, it can be configured to do any number of processing. Primarily, there's 3 processors. One is the CL filter processor, which can filter the events based on what events we're interested in. So there's a CL expression where we can filter what kind of events that we're interested in. And there's a transformation processor which transforms the message. We're dealing primarily with JSON here, but the same can be done with Avro and the likes of it. So here we're just transforming the response to a specific payload format that we're interested in. So this is the payload format, which accepts a few variables. For example, we're getting the order quantity from request.body.quantity, and a few other parameters that we're getting right out of the request and response. And finally, we are enabling change data capture for that particular topology. Finally, it will do a change data capture for the entire events based on the message key. So the message key would have been defined using this JSON transform expression. This accepts JSON-ATA, which is going to transform the messages using Kafka Streams. So the output that we saw earlier, sorry, maybe I can try consuming once again if it shows a better output. Okay, this is much better. So each event, let me see here. Okay, this is much better. So each event that we see here, it has both before and after for the individual row level changes. So here we are doing CDC after we have transformed the message. So here the script changes the quantity every few seconds, which means it has done a CDC based on the quantity. We can see that the quantity is different from before and after, but it does a CDC on the entire event. It can also tell us what was changed. I don't think I've enabled that, but it can also tell us what has changed as well. Okay. With that, I think I will conclude here. If there are any questions, and this is also, we'll be making this source available. So this is primarily a demonstration that we've built to demonstrate how you can achieve this with Kong, or rather with any API gateway, and do CDC events right out of an API gateway. This is a demonstration that we've built, but this much bigger platform that we've also built, but I'm not going to talk about that. So feel free to check it out, and if you have any questions,